Hello everyone, welcome back to my YouTube channel. In this video, I want to continue to solve the next three questions from EJU Physics 2018 second session. In my previous video, I already explained from number 1 until number 9. You can check a link on the description box below if you want to watch the videos. In this video, I will explain number 10 until number 12. Okay, let's start from number 10. In this question, we have a graph that represents a relationship between displacement y of a medium and position x for a longitudinal wave, propagating in the positive direction of an x-axis. So the wave propagates to the right, the positive direction of an x-axis. Here, y is a positive when displacement is in the positive direction of the x-axis. At which point, A until H in the figure is the velocity of the medium at its maximum magnitude. So we want to find the point where the velocity of the medium is maximum magnitude, with its direction being in positive direction of the x-axis. From 1 until 4 below, choose the correct combination. First of all, in this graph, we have displacement versus position for a longitudinal wave. To explain this question, I think I need a diagram. Let me show you a diagram. I have a diagram like this. This is the diagram for a longitudinal wave, where the vertical axis represents the displacement and then the horizontal axis represents distance. The same diagram as the one above here. Okay, if you see from this diagram, the top picture is the position of the medium or the particle of the air before the wave is traveling. So this is the particle of the medium, the dot here. And then when the wave or the longitudinal wave travels on that medium, the particle will start to move. As you can see, this red dot moves to the right. This red dot also moves to the right with a smaller displacement, and so on. My point is, if you are given a displacement versus distance graph, you need to know the position of the compression and rarefaction. Compression and rarefaction is the position where the air particle or the particle of the medium is not moving. As you can see here, this red dot is on its position, or I can say that this red dot is not moving. Even though there is a longitudinal wave travels at that medium, this red dot is not moving. That's the position of compression. Same as the position of rarefaction. If you can see here, this red dot is also not moving. That means this position is a compression. After I mean rarefaction, yeah. After compression, of course, we have rarefaction, and then we will have another compressions. So from this diagram, we know that the x-intercept is the compression and rarefaction. So this is the compression, this is the rarefaction, this is the compression, and so on. The question is, how do we know B is a compression or rarefaction? If I know that B is a compression, then I know D must be a rarefaction, and then F is a compression, and then H is rarefaction. So first of all, I need to know whether B is rarefaction or compression. Basically, to know or to see whether this point is a compression or rarefaction, you can see from the displacement of the particle before that point or after that point. As you can see from this diagram, this is the compression. The particle before compression is moved to the right. Since it is moved to the right, if we assume positive is the direction that is to the right, so if this point is a compression, then the particle before that point must be moved to the right. And then the particle after that point, we talk about this compression, yeah? The particle after that point must be moved to the left, like this. Since it is moved to the left, then the diagram is below the x-axis, and so on. So, if you see from our graph here, the particle before B is in positive y-axis or is above the x-axis. That means the particle before B is moving to the positive direction, which is to the right. Since this particle is moving to the right, and then of course the particle after B is moving to the left because they are located below x-axis, that means B is compression. So I already know here B is compression. Of course D is rarefaction, and then F is compression, and then H is a rarefaction. The question wants us to find the position where the velocity is maximum. Of course, the velocity is maximum not at compression nor rarefaction, sorry, yeah. I repeat it once again. The velocity of the medium at its maximum magnitude, of course, not in the position of compression or rarefaction. Why? Because in compression and rarefaction, the particles of the medium are not moving. So in here, and here, the particle of the medium is not moving. They are at rest. That means if we want to find the maximum magnitude of velocity, of course it is not at B, D, F, and H. So I can eliminate answer 2 because B and F is the compression and D and H, which is rarefaction. So this is not our answer. So I need to choose between 1 or 3. 1 is A and E, 3 is C and G. Which one is correct? Of course, we need to choose the one that in positive direction of the x-axis, which is to the right. Positive direction of the x-axis is to the right. The one that is moved to the right is A and E. As I mentioned earlier, the region before compression, if you see from this diagram once again, the region before compression is the region where the particle is moved to the right. And then the region after compression is the region where the particle is moved to the left, and so on. So for this question, my final answer is number 1. Okay, let's proceed to question number 11. This is question number 10. For question number 11, as shown in figure below, a sound source is traveling with speed vs. Sound source is traveling with speed vs along a straight line while emitting sound at frequency FO from the front and back. So the emitting sound is FO. An observer is traveling in the same direction along the same line with speed VO. So this is the speed of the observer, VO. When the observer is traveling in the front of the sound, the frequency of the sound observed by the observer is F1. As you can see here, in figure 1, the frequency that is observed by the observer is F1. So I think I will write down here the frequency observed by this person is F1. And then for the second figure, when the observer is behind the source, the observed frequency is F2. So for our second figure, this person will observe frequency F2. The question is, what is F1 over F2? We want to find the ratio of F2 over F1, yeah, not F1 over F2. We want to find the ratio of F2 over F1. Of course, this type of questions can be solved by using Doppler effect. We can use Doppler effect. The formula of Doppler effect is F observed, O here mean observed frequency, F observed is equals to V plus or minus VO over V plus or minus Vs times Fs. I will repeat it once again. FO is the observed frequency, VO is the speed of the observer, Vs is the speed of source, Fs is the frequency of source, and V is the speed of sound. Basically, this is the basic formula for Doppler effect. Sometimes we getting confused when we need to determine which sign that we use in our condition. So let's say in figure 1, should we choose positive in the denominator or negative and in denominator? Sometimes we are getting confused for the sign. I have a little trick for you. If you want to use Doppler effect and you are getting confused how to determine the sign, usually we can use this method. This is a little bit trick for you, yeah. When I use Doppler effect, instead of this general equation, I usually use this one. FO is equals to V minus VO over V minus Vs Fs. I usually use this one, and then I will make a sign convention. For example, for figure 1, the direction from source to observer is always assumed to be positive. So this is the positive direction of velocity. This is positive. So when Vs is to the right, that means Vs is positive. VO is also to the right, that means VO is positive. So for the first case, if I use this formula, the observed frequency, which is F1, is equals to both VO and Vs in the same direction is as my sign convention. I repeat it once again, both VO and VS in the figure 1 is in the positive direction of my convention or my assumption. That means V minus VO over V minus VS times the frequency of source. In this question, the frequency of source is FO. So don't get confused, yeah. Frequency of source in this question is FO. FO. This is the observed frequency for the first figure. And then for the second figure, we use the same assumption. As I mentioned in figure 1, the direction from source to observer always assumed to be positive. So instead of to the right, assumed to be positive, in figure 2, we assume the positive direction is to the left. That means, since VO is in opposite direction with our assumption, that means when I put VO in our equation, I should use negative side. So negative VO. Also for VS, since VS to the right and our assumption, our positive direction is to the left, that means when I put VS in our equation, I should use negative. So for F2 is the observed frequency, is equals to V minus VO over V minus VS times the frequency of source. The frequency of source is FO times FO. This is the observed frequency for figure 1, and then this is the observed frequency of figure 2. And then if I want to find F2 over F1, if you see from these two expressions, I think you can find it by yourself. If I continue a little bit, F2 over F1 is equals to, my F2 is V plus VO over V plus VS times Fs over my F1 is V minus VO over V minus VS times Fs. Of course, we can cancel out Fs here. And then if you express this as a single fraction, you will get V plus VO V minus VS over V plus VS V minus VO. If you rearrange the position, then our final answer is number 1. So this is a little trick for you guys who still confused when you want to use Doppler effect. So instead of using plus minus here, I usually write it down minus at first, and then when we see the diagram, we can find out VO and VS should be positive or negative. Okay, this is for question number 11. Let's proceed to the next question, which is the last question that I will explain in this video. Question number 12. As shown in the figure below, so we have a figure below here. This is kind of a double slit, yeah? Like a young double slit. Let us read the question first. A plane mirror is placed horizontally and a panel with slit S and a screen are placed vertically at the edges of a mirror AB respectively. Okay, as you can see from this diagram, you have a slit S, and then you have a mirror AB, and then you have screen. The panel which contains slit and the screen is in vertical direction, or are placed in vertical direction, while the mirror is horizontal. And then the distance between A and B is L. As you can see here, the distance between A and B is L. And then the distance between S and A is D. The distance between slit to A is D. Monochromatic light of wavelength lambda is directed from the left of S. So we have a monochromatic light directed from the left to our slit. And then bright and dark bands form on the screen as a result of interference between light that passes through S. I think I need to highlight this one. And directly reaches the position X on the screen, and light that passes through S reflects at point C on the mirror and reaches X. So, if we want to see interference pattern, we need two source of wave. If we want to see the interference pattern on the screen, we need two source of wave. The first one is the wave that is directly from S to X, and then the second one is the wave that is from S reflect to C, and then it will go to X. So basically we have two source of wave. The first one is directly from S, the second one is by reflected at point C. Due to reflection by the mirror, the phase of light changes by pi. This is the important thing. When there is a reflection, the phase of the wave must be changed by pi. It is inverted. So the wave that is directly from S to X and the second wave here are not in phase. They are out of phase because the second wave here already reflected at point C. So the phase difference between our first and second wave is pi, which is out of phase. Okay, let's continue to read the question. The light reaching X after reflection at C can be thought as light whose phase differs by pi from the light that passes through S. This is that I mentioned earlier. That directly reaches X after passing through hypothetical slit S prime, distance D vertically below A. So, these two waves can be assumed. The first one is from the upper slit, and then the second one can be assumed coming from the hypothetical slit below here. So basically this question is really similar with the Young double slit, but if we talk about Young double slit, the phase difference between our wave is zero, or we can say that the phase difference is in phase. That is for normal Young double slit. But in this question, instead of our two waves are in phase, they are out of phase. And then assume blah blah blah, assume that the slit is sufficiently narrow and D and X are extremely small compared with L. This is the general assumption that we use when we talk about Young double slit. The question is, what is X? We want to find X. What is X? Basically, X is the distance between B and the bright band. So if I assume point X here is the bright band or the first bright, this is the first bright, so I need to find this X. What is X? Okay, so we want to find the fringe separation or X. Basically, as I mentioned earlier, this question is really similar with Young's double slit. The only difference between this question and Young double slit is, in this question, our waves started out of phase. For Young double slit, our waves are in phase. That is the only difference between this question and Young's double slit. So I think, of course, we can use the formula of Young's double slit. If you remember the formula of Young double slit, for a bright fringe of the normal double slit, our formula is A X over D is equals to N lambda, where N is equals to 1, 2, 3, and so on. And then for dark fringe, our formula is AX over D is equals to N minus half lambda, where N is also 1, 2, 3, 4, and so on. This is our formula for Young's double slit, where A is the slit separation, so this is A, slit separation. X is the distance from the central fringe or central bright to bright or dark, if we talk about dark fringe. And then D is the distance from the slit to the screen. So in this question, D is equals to L, A is equals to 2D. In this question, A is equals to 2D, and then capital D is equals to L. Lambda is wavelength, and then N is the order of bright or dark. N is the order of bright or dark. This is the basic or the general formula of Young double slit. This formula is used when the light are in phase. So we use this formula if our wave or our light are in phase. Of course, we cannot use this equation or this formula to solve this question, because in this question our waves are out of phase. Instead of in phase, they are out of phase. So for out of phase waves like this, we just change the condition. So instead of N lambda for bright, we use N minus half lambda. And then for dark, we use N lambda. So in this question, I will use this equation. Young double slit like this. You have to remember, we use Young's double slit if our source are in phase. Since our source in this question are out of phase, just flip it. Okay, so if I want to find x, I can use this equation. Because x is the distance between B and the bright band that is nearest to B, that means we talk about the first bright, that means n equals to 1. By using this equation, I think we can obtain the answer. Okay, let us substitute A. A is equals to 2D. And then times x over d. D is equals to L. Equals to, n is 1 because we want to find the first bright. The nearest to B is the first bright. Minus half times lambda. So I will get 2d x over L equals to 1 over 2 lambda. That means x is equals to lambda L over 4d. So my final answer for this question is number 1. Okay, that's it for this video. I really hope you guys can understand my explanation. And if you have a question, you can drop it in the comment box below. Thank you very much guys for watching this video till the end. I hope I see you guys on my next video. Bye bye.